Chapter 10, Electron Transfer. What is electricity? We use electricity every day. Your computer is plugged into electricity. You need electricity to charge your phone. But what exactly is going on when we plug those things into the wall? Well, electricity is actually the flow of electrons. And voltage is the push of those electrons, kind of like water pressure through a hose. Voltage, as you can see in the bottom here, is just a bunch of electrons in a row. So how does the production of electricity occur? Well, at power plants, it's mechanically produced by a generator. There's wound copper wire spinning between magnets. An axle is turned mechanically by a turbine, where you see there's north and south poles. This occurs in chemical reactions as well. Electrons are released by atoms or compounds, and batteries are a perfect example of a chemical-based release of electrons. Because as you know, we don't always have to plug something in a wall. So here's an example of an electron transfer reaction. It's a chemical reaction that transfers electrons. It involves the valence electrons only. The change in charges indicates that an electron transfer has occurred. So here we have calcium plus 2 hydrogen gives us a plus 2 calcium plus hydrogen. So we can identify electron transfer without charges shown. So here we've got 2 hydrogen plus 2 chloride gives us 2 HCl, which is hydrochloric acid. Examine the electron placement for each species. H2 plus Cl2 gives 2 HCl. We can see that each hydrogen atom owns 1 electron, and each chlorine atom owns 7 electrons. You know this from the periodic table. This gives us 2 HCl, where the H atom owns no electrons, and the chlorine atom now owns 8. We use the oxidation state method. This assigns a number of valence electrons to every atom. Numbers are also called oxidation numbers or oxidation states. Let's look at water. This dot diagram is as follows. Okay, we've got oxygen, which looks like it has the 8 electrons, right? And how many electrons does each atom own, though? So here are the rules. Lone pairs are assigned to an atom on which they reside. You can see oxygen owns both pairs completely up here. The bonding electrons belong to the most electronegative atom present. So for electron counting by the octet rule, meaning there should be 8, you can see that the oxygen has the 8 electrons here, and each hydrogen has the 2 electrons. When we look at electron counting by oxidation state bookkeeping, shared electrons are awarded to the more electronegative atom. The oxygen has 8 and each hydrogen has 0, since oxygen is the more electronegative. So how do we assign a charge? We compare the number of owned electrons to that of the valence electrons in that free atom. The oxygen has 6 electrons in a free atom and 8 are assigned, so the charge would be -2. The hydrogen has 1 electron in a free atom and none are assigned, so the charge is +1. So determine how many electrons each atom owns in NH2F. As we can see, the number of valence electrons in the free atom of the element, okay, according to the picture here, fluorine has 7, nitrogen has 5, hydrogen has 1, and hydrogen B has 1. We subtract the number of electrons assigned to the atom by oxygen state bookkeeping. Fluorine would be 8, nitrogen would be 6, hydrogens have 0. With the oxidation state, we're looking at the difference between the number of valence electrons and the number of electrons assigned by oxidation state bookkeeping. We call this the oxidation number. So for water, the number of valence electrons in the free atom of the element minus the number of electrons assigned to atom by oxygen state bookkeeping. So if oxygen has 6 valence electrons and oxygen state bookkeeping says 8, hydrogen has 1 but oxygen state says 0, we can see we have a -2 and a +1. So if N is positive, it means it owns N fewer electrons. It exhibits a positive oxidation number. If N is negative or owns more electrons, it exhibits a negative oxidation number. Remember, these are all artificial numbers and not real charges. So when two atoms of the same element share electrons, the oxidation state method divides the electrons equally. So on the left, we've got 6 electrons, the center is 5, and the right is 7. So here's some steps to assigning oxidation states by that electron bookkeeping method. It's a great resource slide for you. But here's some shortcuts. Everybody loves shortcuts, right? So the oxidation is the most abundant, naturally occurring form is assigned to 0. The oxidation state of oxygen in a compound is almost always -2. The oxidation state of hydrogen is almost always 1. Group 1A elements are always +1, 2A are always +3, and the oxidation of a monoatomic ion is equal to the charge of the ion. And number 7, the sum of the oxidation states for an ion or a molecule is the overall charge of the ion or molecule. So on water, we get a -2, a +1, and a +1. Our sum is 0. Okay? For OH, the little negative after it, you can see the oxygen's -2, the one hydrogen's +1. That gives us a -1. Then we have the halogen rule, way over on the other side. Any halogen atom in a compound most likely has an oxidation state of -1. So in the case of CHBr3, we have a hydrogen, 3 bromines, and a carbon. The oxidation state shows that hydrogen is +1, all the bromines are -1 because they're halides, and there's really no rule for carbon. He gets a little tricky. We know the sum is 0 because there's no charge on it. We're now able to figure out the charge on carbon because all of these added up together need to equal 0. So in this case, if +1 and -3 would give us a -2. So we know that carbon would be a -2 to get to 0. So what is the oxidation state of manganese in the compound KMnO4? The oxidation state, going back. We would need to look at each element and their oxidation state. I encourage you to work on this and find the answer in a future course announcement. What would the oxidation state be of carbon be in the compound CHBr3? Oh, you know what? Sorry about that. This one, here's the answer. Ignore the top of this. The best answer is +7. K has a +1. Oxygen is -8 because there's 4 of them and they're -2 each. We don't know manganese. We know the total charge is 0. So 0 equals +1 plus a -8. When we solve for x, manganese is +7. Here's the next one that it kind of skipped over. What would the oxidation state of carbon be in the compound CHBr3? The rule says that the sum of oxidation states must equal 0. So we know that we have a -3 plus 1 plus x equals 0. If x equals +2, the charge of carbon would be +2. Here are the steps for that one. Here are the assigning oxidation states by shortcut method. I would recommend hanging onto this slide and really memorizing this one. So what would the oxidation state of carbon be in the compound C2H4O2? Use your shortcut steps and push play when you're ready for the answer. Well, we know oxygens are -2. Okay, so that's from rule 2. All the hydrogens are +1. That's rule 3. We don't have a rule for carbon, but the sum must equal 0. So it happens that the carbon's oxidation state is 0. 2 carbon plus 4 times 1 minus 2 times -2 equals 0. So carbon equals 0. So next we'll look at the electron transfer reactions. This is any reaction in which an oxidation number of an atom changes. And the redox reaction is a reaction that occurs both reduction and oxidation occur. In reduction, there's a gaining of electrons and a decrease in the overall oxidation state. So here we've got CH4 plus 2 O2 is going to CO2 plus water. The oxygen is reduced, okay, 2 minus 2, and it gains electrons. In oxidation, this is the loss of electrons, an increase in the overall oxidation state. Carbon is oxidized. It loses electrons. The oxidizing agent is a substance that oxidizes something else. So oxygen oxidizes methane and is reduced. You can see methane is oxidized. The reducing agent is a substance that reduces something else. The reducing agent, CH4, reduces oxygen and itself becomes oxidized. So which substance is the oxidizing agent and which is the reducing agent in the following? The reducing agent would be, it reduces Br2 and becomes oxidized. So the oxidizing agent oxidizes P4 and is reduced. So each bromine gains 1 electron, which is the reduction, and each P loses, or phosphorus loses 3 electrons, which is oxidation. Identify the oxidized species in the following chemical process. Hit play when you're ready. So iron is the oxidized reagent here. The oxidizing agent or oxidant is the substance which reduces or gains electrons in the equation. Each NO3 molecule has 1 spare valence electron, so it donates it to the copper to bond. However, as iron is a stronger oxidizing agent, meaning it accepts electrons better, the NO3 donate their electrons to it. This leaves the copper metal all by itself. We can use oil rig, which is short for oxidation is loss, reduction is gain. A galvanic battery or galvanic cell, also known as a battery, is a good example to show how a wire allows a path for the flow of electrons. Here's a zinc copper battery. We can see we've got a zinc solution here. We got Zn2 plus and SO4 2 minus with a salt bridge, a zinc electrode, and a copper electrode. The salt bridge is a conductive component completing the cell, and it maintains charge balance between the two sides. We've got spectator ions that they're not directly involved in the redox reaction, and we get electrodes, which are metal strips submerged in those solutions. So here's how that battery generates the electric current. A zinc atom gives up 2 electrons to become Zn plus 2, which enters the ZnSO4 solution. Here's that oxidation reaction. The electrons flow through the wire from the zinc electrode to the copper electrode. The electrons reduce a Cu2 ion from the solution to a Cu atom. The Cu atom plates out on the electrode, which is the reduction reaction. Here's how the salt bridge completes that circuit. As the oxidation reaction produces the Zn2 ions, SO4 2 minus ions flow in from the salt bridge to prevent a buildup of a positive charge. And as the reduction reaction consumes copper ions, sodium ions flow in from the salt bridge to prevent a buildup of negative charge. A standard cell battery is actually a redox reaction in a can. Okay? Reactants are MnO2 and zinc. A semi-moist paste containing NH4Cl acts as the salt bridge. Here's what it looks like inside the cross-section of a dry cell battery. Okay, we got the MnO2 paste around the graphite core, the NH4Cl and ZnCl2 paste, and a zinc metal can. So we can see the reducing agent is zinc and the oxidizing reagent would be the 2MnO2. A wire connecting terminals allows the electron flow. So here we have our battery and our wire. So the anode, okay, the negative, electrons travel from the anode towards the cathode, which is the MnO2. So electrons move around, producing the power. The cathode is the positive. Okay, so cats are positive. Remember we talked about that earlier, which is the MnO2. And the anode is the negative, or the zinc. What about a lithium-ion battery? Everybody's got those in their phones nowadays, right? This is made of cobalt, or the cathode, and the lithium atoms in a graphite carbon, which is the anode. And they're separate. There's a separator membrane. So we've got the positive cobalt 4 oxide and the separator, and then the anode, which is graphite carbon. During discharge, the following occurs. Lithium ions give up electrons, and the cobalt is reduced to CO+3, and the lithium with the cobalt and the O2 is formed. Then we have fuel cells. This is a battery in which one reactant is a combustible fuel and the other is oxygen. Electron flow from active metals to less active metals can actually help preserve a few things. And we're going to learn about how those things work and some of the things that you're familiar with here in a second. But electrons will flow from magnesium to zinc. Electrons will not flow from zinc to magnesium. Here's a test to find out which metal is more active. If we put zinc in a magnesium solution or magnesium in a zinc solution, you can see the difference there. In electromotive force, or the EMF series that we've used to see which metal is more active, we can actually visually see which one, but there's actually an EMF series. You can see this chart on the side. The most active lose electrons most easily, which would be lithium, and the least active loses electrons least easily, which would be gold down on the bottom. So there's increasing activity as we head up. So what will happen if a piece of zinc metal is placed in a solution of Al3+ ions? Al is higher in the EMF series, or aluminum, so zinc will not spontaneously give up its electrons. Thus, there will be no reaction. Oxidation is the combining of oxygen, or the formation of rust in an oxidation process. Here we've got 4 iron plus 3 oxygen, giving us 2 Fe2O3, iron oxide. Fe has an oxidation state of 0. The Fe and Fe2O3 has an oxidation state of +3. Electron rules still hold true here. So here's the oxidation on the Statue of Liberty. Okay, copper slowly combines with oxygen in the air. Okay, we see that happening here. The ions in the form of copper hydroxycarbonate and copper hydroxysulfate. The formed Cu+2 could oxidize the iron skeleton of the statue, endangering the structure. So here's what's happening. We got the copper skin of Statue of Liberty, right? She's getting rained on. Then there's an iron skeleton on the inside, and it's corroding. So here's how the process works. The copper oxidation, when exposed to air and seawater, copper oxidized to Cu+2 in the absence of iron. This process would form a protective patina coating. With copper reduction, when the copper contacts the iron, the Cu+2 can accept electrons from iron, reducing back to Cu. Alternating oxidation reduction of copper is now cyclic. So the sacrificial iron oxidation is where the iron undergoes sacrificial oxidation to feed electrons into the copper redox cycle. Another example is metal pieces being designed to oxidize in place of other metals. So think of huge cruise ships or big ships going back and forth from other countries. We need active metals to help stop some of that oxidation. Magnesium is very common. We can see there's magnesium plates on the steel hull of ships, and we've got a steel utility pole and a conducting cable with a magnesium stake for that as well, to stop some of that oxidation from occurring.